Thanks, Russell. So we'll talk about joint work with James Lee and with Cheyenne Always Garan on higher order Cheeger inequalities. So this is a work about spectral graph theory. So let me start by just by enunciating what are the most basic results in spectral graph theory and where the question that we address comes from. So let's say that we have an undirected regular graph. So all the results that I will talk about hold for general weighted, not necessarily regular graphs, but some definitions are easier in the regular case. Although all the results will hold for undirected graphs only. So let's define the Laplacian of a graph as this matrix, the identity minus the adjacency matrix of the graph divided by the degree. And in a moment, we'll see why this is an interesting matrix to look at. For now, let's just note that it's symmetric and real. So this means that all the eigenvalues of this matrix are also real, possibly with multiplicities. So let's say that lambda 1 through lambda n are the eigenvalues of this matrix. And let's say we sorted them in a non-decreasing order. So some basic facts that connect the eigenvalues of this matrix to properties of the graph are that, well, lambda 1 is always 0. But so 0 is always an eigenvalue of this matrix. But the multiplicity of 0 as an eigenvalue is precisely the number of connected components of G. And though this is a different story, it's also known that lambda n is smaller than 2, and that lambda n is 2 if and only if at least one of the connected components of G is bipartite. So if we think of the eigenvalues of L as solutions of equations of the form Lx equal lambda x, the fact that, or as roots of the polynomial determinant of, what is it? L minus I, L minus lambda I. So it's really remarkable that purely combinatorial properties of a graph, such as which vertices are connected to which other, so how many connected components you see in the graph, or whether or not there is a two-coloring of the graph in which, or a subgraph in which every edge is bichromatic, would be determined by the roots of these polynomials or the solutions of this equation. Although when we look at other characterizations of the eigenvalues of this matrix, these facts will be much more transparent. So but those are sort of extremal facts. So here lambda n is always set most 2, and it's exactly 2 if and only if some subgraph of G is precisely a bipartite quantity component. Or here lambda k is exactly 0 if and only if there is a partition of the vertices of G into k subsets so that absolutely no edge goes across. Now, a special case of the first fact is known to have also a sort of more robust version that doesn't talk about only the extremal case, but also talks about near extremal cases, which is Cheeger's inequality. So a special case of the first fact is that lambda 2 is 0 if and only if G is disconnected. And informally, the discrete, the graph Cheeger inequality says that, so this was proved in slightly different version by Alon in one direction, Alon and Millman in another, is that lambda 2 is small if and only if G is not an expander. So let's see the precise quantitative version of this fact. So if you have a graph, then and as we said before, G is deregular. So we'll say that the expansion of a set of vertices will be the number of edges that leave the set of vertices. So the number of edges with one endpoint in S and one endpoint in the complement of S, divided by something that up to a factor of 2 is the total number of edges that are incident on the elements of S. Another way to think about it is that if we pick a random element of S and then we move to a random neighbor, this is the probability that this random neighbor will be outside of S. So it's the probability of leaving S in a random walk condition on starting in S. Okay, and then the expansion of a graph is the minimum of this quantity over all sets of vertices of size less than half the total. Okay. So in particular, the expansion of a graph is 0 if and only if the graph is disconnected, because it means that there is some subset of vertices that has 0 outgoing edges. But more generally, it's small if the graph has some kind of bottleneck where there is some set of vertices and the complement, both very rich in edges, but with very few edges going in between. So then the precise statement of this fact is that the expansion of G is both upper bounded and lower bounded by lambda 2. So it's at least lambda 2 over 2. It's at most square root of 2 lambda 2. Or maybe the 2 is outside of the square root. So they are, so those quantities, one of those quantities is small if and only if the other is, up to this square root approximation. And so so both directions of this inequality are very useful. This is saying that if we want to explicitly construct a graph that has this expansion property, one way to go about it is to construct a graph in which the second eigenvalue is bounded away from 0. And in some cases, that's an easier way to do it. But it also says that if you are studying a graph and we want to know whether or not lambda 2 is bounded away from 0, which could be useful if you want to estimate the mixing time of random walk in the graph, one way to go about it is to lower bound the expansion of the graph. Actually, in some cases, easier than explicitly computing the eigenvalues. In terms of algorithm design, when a graph is not an expander, so it means that there is a sparse cut in the graph, which is a useful thing to find, because in one way it can be seen as it can be a step in a clustering algorithm, because if edges represent similarity between points, this cut will show a partition of the vertices into two subsets such that within each subset the vertices are similar to each other, but within different subsets they are not so similar. In fact, a very popular image segmentation algorithm proceeds by iteratively finding cuts of this form with vertices representing pixels of the image and edges similarity measured. But this problem is NP hard. It's also not so easy to approximate. And the proof of this direction of the inequality is constructive in the sense that not only it shows that the expansion of G is at most square root of 2 lambda 2, but so the proof of this direction also shows that given the eigenvector of lambda 2, one can find in linear time nearly linear time a set S such that the expansion of S is at most square root of 2 lambda 2. But then by the other inequality, this is at most square root of 4 of the expansion of G. So this means that by finding the eigenvector of lambda 2, which also can be done at least approximately in nearly linear time, and then applying the constructive version of this proof, one can find, well, not exactly an optimal cut, but one whose sparsity is small if a sparse cut exists. And in fact, that's the spectral partitioning algorithm is the one that is most used because of its efficiency when wanting to find just one set of small expansion in the graph.
How easy is it to find eigenvectors?
Well, the analysis works also if what is given is not exactly an eigenvector.
Down to the quadratic form, I think, right?
Yeah, as long as the Rayleigh quotient is bounded, the algorithm will work. So for that, any iterative method like the power method or the, how is it pronounced, Langkos? Langso method will, what's that? Lanchos will be good enough. Right. So given that there are although and so this was known since so this theory was developed in the 80s. So given that there are so many interesting consequences of having this robust version of the k equal to case, it could be interesting to see if one can get a robust version for every k. So what we so let's define a version of expansion of a graph. So the definition of expansion I gave before talks about partition a graph into, well, finding a subset of the vertices. So implicitly finding two sets of vertices with few edges going in between, which is the set and its complement, which corresponds to the extremal case in which the graph is disconnected, so it has at least two connected components. So to look at what could be the combinatorial analog for general k, we'd have to look either at a partition of the vertices into k subsets or finding k disjoint subsets. So let's say that expansion for k of a graph G is the minimum over all disjoint. So for now, let's say it's not a partition, just disjoint sets. Of the maximum of their expansion. So it means that for a graph to have k expansion epsilon, there must exist k disjoint sets such that each of them has expansion at most epsilon. So for k equal 2, that's the same as the expansion of the graph, because if you find a set of size less than n over 2 that has expansion at most epsilon, its complement will also have expansion at most epsilon, because in the definition of expansion, you have the same numerator but a bigger denominator. So what we prove is that this parameter we'll write it here so it can stay. So we prove that this parameter is at least lambda k over 2, and it is at most k squared times the square root of lambda k. So this parameter is small if and only if lambda k is small. And if we maybe kind of, so we see the case k equals 0, it means that you find k disjoint sets, each of which is disconnected from the rest of the graph, so that the graph is at least k quantity components. So another alternative, so another generalization of the definition of expander would be the same, but minimizing overall partitions. Because in the standard definition of the same quantity, because in the standard definition of expansion, we're really thinking about a partition of the graph into two subsets, because we look at a subset and its complement. But once we have k disjoint sets, each of small expansion, if there are some leftover vertices, we can put them into the bigger set, and this only affects the expansion of that set by a factor of k. So this, this is just a corollary. This other quantity is also small if and only if lambda k is small. And as before, yes? Oh, no. It means that there is an absolute constant that multiplies k squared. No, I'm just saying that there exists an absolute constant such that we have this.
K squared is first, right?
And this is true for every k greater than 2.
Is the dependency on k squared, right?
No, in fact, we don't know.
It's a reasonable constant.
Pardon me?
It's a reasonable constant. Like undirected.
Oh, yeah, no, maybe it's more like 6 or 4. Yeah. Okay, and the proofs are constructive. So given the k eigenvectors or given k nearly orthogonal vectors, each with small Rayleigh quotient, we can find those sets. So we can also show that.
Is it enough to find the linear strings,
So we can also show that so here we lose this compared to square root of lambda k, which is what we might expect as a generalization of the original Cheeger inequality. There is this factor of k squared that we lose, or k cubed if we want a partition. So there's another result in which we lose only log k instead of k squared. However, the upper bound does not relate anymore to lambda k, so it's not a if and only if. It will relate to lambda of 1.1 dot times k, or k plus some constant times k. And and kind of we lose more and more depending on how small we want this constant to be. It's worse, right, because this is, there it was k. Yeah. And Lewis, Raghavendra, Tetali, and Vempala independently proved something similar. So they also show that this parameter is at most some constant times the square root of lambda of some constant times k. So in their case, this could be arbitrarily close to k. In their case, this might be like 5 or 6 times k, but it's in the same ballpark. Yeah.
Just for the first line, I'm curious. Can you actually set that thing, the leading constant, to be really small by making delta be super constant? Can I set delta to be k and then?
Oh.
And then have 1 over.
Well, let's say no. I think we only did the analysis for delta less than 1. I'm not sure. Yeah. But say if you set delta to be 1, this will be an absolute constant. I don't know if you can make it arbitrarily close to. Yeah, I don't know what the limit of the constant would be if you allow the error to be bigger. And it's so those results are tight in the sense that there are families of graphs where this parameter is a constant times the square root of say lambda 2k times log k. So even allowing some slackness between how many eigenvalues you can work with and how many sets you are looking for, a loss of log k compared to what you might hope for, which is the square root of the eigenvalue, is unavoidable.
What about compared to lambda k? Is a loss of k or
That we don't know. So it could be that this loss of lambda k is achievable without this slackness. which I think is more likely. But it could also be that there is a stronger lower bound that we haven't thought of.
What's the lower bound for? I mean, this is for a specific graph, right?
This lower bound, that's for the noisy hypercube, which is not, yeah, I guess which is regular. Anyway. But all the bounds hold for non-regular graphs as well.
So do these new constructions, new replacements of noisy hypercubes?
It's not clear. So yeah. So let me say these other results. So one of the let's say an implication of these tighter results is that if we take any graph, it is possible to find a subset of vertices whose expansion is at most some constant independent of k times lambda k log k, and whose size is at most some constant times number of vertices divided by k. I guess here k is not the same k as before, but it's like so take, say, this result with delta equal 1. This is saying that you can find k disjoint subsets, each of expansion at most lambda 2k times log k. So now call k 2k. So it means that you can find k over 2 disjoint subsets, each of them having expansion at most square root of lambda k log k. So this constant, we could make it 2 if we want. So the existence of many small eigenvalues implies that there is a small set that is non-expanding. So Aurora, Brack, and Stoyer, maybe this corner is hard to read from the direction. So yeah. So let's make this comparison here. Okay. So what we got in our paper and what's in this independent result of Luis Raghavendra, Tetali, and Vempala is the existence of a set of expansion square root of lambda k log k and size at most say 2 times the number of vertices divided by k. And in Aurora, Brack, and Stoyer, they have a set of expansion let's say square root of lambda k over alpha and size at most number of vertices to the 1 plus alpha divided by k. Okay. So we may think of the impossible goal, but like for comparison, that we would like the expansion to be square root of lambda k and the size to be number of vertices divided by k. So if we were able to prove our main result with absolutely no loss in the expansion, this is what we would get by looking at the smallest of the k disjoint sets. Okay. So this is impossible, and those two results give kind of a couple of different directions in which something similar can be achieved. So if we want the expansion to be as small as it can be given the spectral information, so square root of lambda k, well, let's say up to a constant, then the size of the set will be v over k times v to the alpha. Okay, so we'll lose a fixed root of the number of vertices in terms of the size. So for this to be something, k itself will have to be some constant root of v. Here, the size of the set is as small up to a constant as one could expect, but the expansion is worse by a factor of square root of log k. And as I said, this result is tight, and recently it has also been shown that this result is almost tight, so that if you want to lose only a constant factor in the expansion, what you lose in the size has to be something like 2 to the power of a constant root of log v. So more than log v, and definitely something that depends on v and not on k. This is impossible. So you cannot hope simultaneously to have optimal size and optimal expansion.
With no leading constant.
Even with a leading constant. Yeah. So, yeah, not with a leading constant independent of k.
So it's impossible, whatever C you choose is impossible.
Yes.
You have a construction is counter.
Yes. So we are there is a family of graphs for which if you want to find k disjoint set, well, even if you want to find the way I said here, there is a construction that if you want to find k disjoint sets, at least one of them will have to have expansion that grows like square root of lambda k, even square root of lambda 2k times log k. But in fact, in the proof, it shows that this is necessary not just if you want to find k disjoint sets, but even if you're looking at a set of size n over k. So then, if it's impossible to find a set of size n over k with this expansion, for a stronger reason, it's impossible to find k disjoint sets with that expansion. Well, so those two results and the match, or in this case, almost matching lower bounds, also shows kind of how close you can get to this. If you want to stay very close in terms of the expansion, you have to lose something at least in the ballpark of a constant root of v in the size. And if you want to stay close in the size, you have to lose square root of log k in the expansion. It's not completely clear what interpolates between those two results. For example, it could be that by losing log k in the expansion, maybe one can lose only log n in the size. This kind of in between, right, Sanjeev? This is completely. This is not doesn't contradict any of the lower bounds. I think. I think it's compatible with what we know about possibilities and impossibility results, that you could have expansion lambda k log square root of lambda k log k and size v log v divided by k. Okay, but yeah, that's
once you throw in log.
Yeah. No, but I think that would be enough to refute the unigame's conjecture, because, well, no, sorry, it would be enough to refute the hardness of small set expansion in the regime where the analogous unigame's conjecture.
If there's no penalty in the, I see, right, yeah.
Well,
I mean, even just the question of
if there is a small penalty, yeah.
Right.
Oh, I didn't do the calculations. No, but I think the noisy hypercube doesn't rule out even having this with log n here in a different construction to get a lower bound, where here you have to go beyond log n. So to get lower bounds in between, I think I don't even know what graph would be the right lower bound example. Right. So those results were, this result is a model for what kind of trade-off is possible, and raising the question what other trade-offs were possible was one of the motivations for this work. The other is that some of the original Cheeger inequality is at least one explanation for why spectral partitioning algorithms that use the eigenvector of lambda 2 seem to work very well. Or at least it's a worst case analysis of partitioning algorithms that use the eigenvector of lambda 2. Now there are clustering algorithms that also work very well in practice that are based on taking the bottom k eigenvectors of the Laplacian, and then using them to those eigenvectors are used to get an embedding of the vertices in k-dimensional real space, because every eigenvector assigns a real number to each vertex. So if you have k eigenvectors, you have k real numbers for every vertices, and you can think of it as being a mapping of the vertices in a k-dimensional space. So so something has been observed in practice is that if graphs have some good k clustering, so if there are k subset of vertices all closely interconnected with few edges going out, in this embedding, one will see the vertices mapped more or less in k small regions of space. So then a geometric clustering algorithm will find a clustering in the graph. And this has been analyzed formally in a random model where a clustering is planted into a random graph. But as I will describe our proof is based on finding regions in this embedding such that each region corresponds to vertices having small expansion. So that's also a kind of worst case analysis of algorithms that are based on embedding and then geometric partitioning.
Did
Yeah.
you say that you analyze that precise algorithm?
No. So our, in fact, that precise algorithm, I don't think it can have a good worst case performance.
Yeah.
But it's a worst case analysis of the approach of using the k-dimensional embedding and then reasoning geometrically about embedding. Yes? This will not happen in general. So if you construct a random graph in which there is a planted clustering, say you divide a vertex into k subsets, and then for vertices in the same subset, you pick random edges with high probability, and for vertices in different subsets, you pick edges with low probability, then this embedding will put the vertices in the same cluster almost in the same point. So the embedding will look like really k small regions. But for general graphs, this could look very different from that. Okay. Okay, given that I have a lot of time, I will present the proof in a leisurely pace. So, so my plan would be to first describe how you argue that lambda 2 equals 0 if and only if G is disconnected, which is very simple. But at least one starts looking at how the eigenvalues of the Laplacian have anything to do with properties of combinatorial properties of the graph. And then look at how this argument can be generalized in two different directions to give previously known facts that lambda k is equal to 0 if and only if G has at least k connected components, and that and a standard Cheeger inequality that the expansion of the graph is upper bounded and lower bounded by lambda 2. And then sort of combine ideas that go in these two generalizations to get our result. In particular, I will present the fact that lambda k equals 0 if and only if G has at least k quantity components in an unnecessarily complicated way, but that will include a good part of the ideas that we have in the general case. Okay. Okay, so let's see how one computes the eigenvalues of a real symmetric matrix. So the smallest eigenvalue of a real symmetric matrix is the minimum over all non-zero vectors of this normalized quadratic form. And then lambda 2, so let's say that x1 is a minimizer. Then lambda 2 will be the minimum in the orthogonal space of x1 of the same quadratic form. So let's say that x2 is a minimizer. And then lambda 3 will be the minimum in the space orthogonal to x1 and x2 and so on. So this is one characterization of the eigenvalues of a Hermithian matrix, in this case, a real symmetric matrix. So, so now this form, so now it comes to why the Laplacian is a useful matrix for graphs. If one expands it out, so this is the adjacency matrix of the graph. So this is twice the summation over all edges of the difference of the value of this vector x at the endpoints squared, normalized by the size of the vector. Okay. So this is because so this is equal to this, and when opening up this expression, one immediately gets the numerator. There is a d here because L was defined to be so one gets this expression after multiplying by d. So dividing by d normalizes. And we'll call this the Rayleigh quotient of a vector x. So since the numerator is a sum of squares, we really see that all the eigenvalues of this matrix will have to be greater than or equal to 0, because those quotients will always be greater than or equal to 0. AUV is the adjacency matrix of the graph. So AUV is 1 if UV is an edge, and it's 0 otherwise. So the Laplacian is the matrix that has ones on the diagonal, and then in the off-diagonal places as either -1/d if that's an edge, or 0 otherwise.
You have there every edge only once, I guess, usually.
Oh, the edges are there twice because it's sum over UP, right? So then you
Yeah,
get
and I
the-
think shouldn't it be only once? Doesn't matter. Because
Oh, because you get the double product only once, right? So it's like half this. Or okay, let's do this. Okay, so this is always greater than or equal to 0. And a minimizer is to set this vector to be the same constant in each coordinate. Because then the numerator will be 0, because all those differences will be 0. So a possible minimizer is to set x1 to be all 0. So then lambda 2 will be the minimum over all x's that are orthogonal to this vector, which means all the x's whose entries sum to 0. So if lambda 2 is equal to 0, it means that we have some vector x whose entries sum to 0 and whose Rayleigh quotient is 0. But what does it mean for the Rayleigh quotient to be 0? It means that this summation is 0. Okay, so let's write this way. So this means that for every edge, the values of this vector must be equal at the endpoints. But then by induction, it means that if there is a path from u to v, then also those must be equal. But this is a non-zero vector whose entries sum to 0. So some entries will have to be positive and some entries will have to be negative. So if we pick S to be all the vertices whose entries in X are positive, well, S will be a non-empty set. And it will be disconnected from the rest of the graph. Because well, it's a non-empty set. It's not the whole graph. And it is disconnected from the rest of the graph, because if you have a vertex with a strictly positive entry in X, it can only be connected to vertices with the same label. So in particular, it cannot be connected to vertices with a 0 or negative label. Okay. For the other direction, actually something that will be useful that also follows from this characterization, and that will be useful later, is that lambda k is smaller than epsilon if and only if there is a k-dimensional space all whose elements satisfy that the Rayleigh quotient is at most epsilon. So this space would be made of the by the eigenvectors. Now, if the graph is disconnected, we can find two orthogonal vectors. Well, actually, let's say this way, there are k orthogonal vectors. So we can find two, if the graph is disconnected, we can find two orthogonal vectors whose Rayleigh quotients are 0. Just set the vector to be the constant 1 on one quantity component and 0 outside, or the constant 1 in the other quantity component and 0 outside. If there are two quantity components, those vectors will have non-zero entries in disjoint coordinates, so the inner product is 0. And since they are constant between quantity components, the Rayleigh quotient is also 0. So this also shows that you get lambda 2 equals 0 if the graph is disconnected. And already it shows that you get lambda k to be 0 if you have k quantity components, because you just do that for each quantity component. So let's see that if you have lambda k equals 0, there must be k quantity components at least. And we'll see that by starting to think about this embedding of vertices into k-dimensional real space given by the eigenvectors. So suppose the lambda k is 0. So this means that there are these k orthogonal vectors, x1 through xk, which are orthogonal. And in fact, let's scale them so that they are orthonormal, because the Rayleigh quotient is invariant by scaling by a constant. And each of them has Rayleigh quotient 0. So now let's define this mapping of the vertices into k-dimensional space by saying that we associate to a vertex the k real numbers that those k vectors. So it's not even necessary that they are eigenvectors. They just have to be orthogonal vectors with 0 Rayleigh quotient, but they could be the eigenvectors. Well, so recalling that that's the definition of a Rayleigh quotient, what we have is that if uv is an edge, then it means that f of u must be equal to f of v. Because for each of those xi's, if the Rayleigh quotient is 0, each of those xi's must be vectors that have identical coordinates in vertices that are connected. And in fact, the same if there is a path from u to v. So it remains to prove that f maps the vertices to at least k distinct points. Because then we can take the pre-images of points in real space to which vertices are mapped and all those pre-images will have to be disconnected sets of vertices because of this property.
So if not, then you can feed into lower dimensional space within.
Yeah, so one way to see that is that this mapping was coming from those k orthogonal vectors. So in particular, the set of points that you map to will have to be truly k-dimensional, because if you had a way of putting them into a k minus 1 dimensional subspace, you would also find a linear relation between those vectors.
So just draw the matrix, right? It's a k by n matrix. We know because from orthogonality, the rank of the rows is k, so the rank of the columns must also be k.
Exactly.
And in particular, there have to be at least k distinct columns.
Yes. But I want to prove it in a more complicated way because this argument doesn't generalize to the approximate case, while the unnecessarily complicated argument I will present now does.
It doesn't even make use of the, I mean, you don't even need orthonormality. You just need
Linear independence.
linear independence, which won't be enough for the Cheeger type of thing, right? Because if they're all very like correlated with each other, but they still have small, that shouldn't be enough.
Yeah. You need to know something about the distance between those vectors. Yeah. Okay. Maybe I'll leave up the definition of Rayleigh quotient for later. Okay, so we will prove that f is isotropic, which means that for every point in k-dimensional space, if we look at the summation of over the vertices of the inner product of g and f of v squared, this will be something that depends only on the norm of z, and in particular it will be equal to the norm of z. So how to think of this? So let's say that we're just looking at unit vectors z, so that there are kind of directions. So f of v is a mapping of the vertices into k-dimensional space, and it's n is bigger than k, right? So those are many points. So this is saying that for every direction that we look at, if we project those points in that direction, and then look at the sum of the squares of those projections, that's the same no matter what direction we are looking at. So this is saying, although it's only a partially correct intuition, that those points are uniformly spread in Rk. That so whichever direction we look at, there are about as many, or there is about as much mass of points in that direction than in any other direction.
It's the covariance, right?
Yeah. Okay, to see this, so what are those inner products? We are so let's say this is z, right? So this is k by n, and those are x1. No, I'm getting this wrong. Okay, so let's think of this n by k matrix formed by the k eigenvectors. So then the rows are the vertices. So when we multiply this matrix by z, we are going to get n-dimensional vector, and this vector is going to be the collection of all the inner products of our images of vertices by z. So if this is the vertex 1, the vertex 2, the vertex 3, and so on, here we're going to see z inner product f of 1 up to z inner product f of n.
Luca, are you just headed towards the convex relaxation for threshold rank?
I just want to prove this this
No,
equality.
Right now, what I'm saying, the generalization you're headed towards is the BRS convex relaxation.
I don't think so.
No, okay.
Well, maybe later you can see if it's the same, but I don't think it's related.
Oh, it's not related.
Yeah. That's so the inner products of the images of the vertices with this vector z are is just what you get by multiplying this matrix by this vector. And in fact, this is basically a linear combination of those vectors indexed by the coordinates of z. What we have here is the norm square of this vector. So we're looking at the norm square of a linear combination of orthonormal vectors. So that will just be the norm square of the coefficients that we use in the linear combination. And so it will be the norm square of z. Okay, so let's restrict ourselves to norm 1. Well, it's, yeah.
If you look at this vector as z1 through zk, then
Yeah, so we are taking a linear combination.
z1x1 plus z2.
Exactly, this is just z1 x1 plus zk xk. So its norm square will be z1 square plus zk square.
So, Luca, is it easier just to, I mean, if you look at it as this matrix vector product, so instead, you know, when you take the squared norm of that matrix vector product, so just multiply it by its own transpose, and then that matrix inside is just this, you know, k by n times an n by k matrix, which is the identity.
Oh, because of the orthonormality. Yes, exactly. Yeah, that's another perfectly good way of saying it. So you get z times identity times z, and so it will be z squared. Absolutely. Okay, so now we'll argue that this means that we have at least k points, because suppose that f is mapping the vertices into only k minus 1 points. So another thing that we know about f is that the summation of the norm square of those points has to be k, because this is just the summation of the squares of the entries of this matrix. So it's the summation of the norm squares of the xi's, and each of them was a unit vector. So if f is mapping all the vertices into only k minus 1 points, there has to be some point in k space such that the summation of the norm square over the vertices that map to, so say this is a point z, the summation of the norm square of the points that map here would have to be bigger than 1. If there are fewer, if the total norm square is k, if you map into k minus 1 points, one of them will have to have summation of norm square bigger than 1. So then just then apply this fact with z being this z normalized to have norm 1. So suppose that there is a point in Rk such that when we look at the vertices that map there, their overall L2 square mass is bigger than 1. Well, then call z prime the direction of z. Then this norm square is the same as this inner product square, because when you take the inner product of a vector by its direction, you get its norm, and then you square the inner product and you get the norm square. But that's in contradiction with the isotropy condition, because it says that condition says that the sum over all vertices has to be 1, and here even just the sum over a subset of vertices is already bigger than 1.
You're basically now showing that there are at least k different rows in this matrix, right? That's another way of saying.
Yeah, but
Saying if the same row repeats many times, then just multiply the matrix by this row, and you're gonna get.
Yeah, but now we are already getting something more. So we are not only saying that this mapping must map to k distinct points, we're also saying that
It has to be somewhat uniform in this way, right?
well, let's say for now that if we look at the images of the mapping, they cannot be covered by k lines, right? Because suppose you had k lines that cover all the points. Then there would be one line such that the points along that line accounts for a norm square bigger than 1. And now let z prime be the unit vector of this line, and then you get exactly the same. So that's already something that is not clear how to get from just looking. Well, sure, that's true. You would still get a lower dimension. Okay. But the okay, so we've proved there are k connected components if lambda k is 0. Now let us see. Russell, you have a question?
So it's traditional to offer the speaker the opportunity to have a 5-minute break at some point.
Okay. Well, if
So it seems like you're at like a transition point. So, but it's also
yeah.
the speaker is free to say no, I don't need a break.
No, actually, it's a good point for a break. I'll just say that kind of the starting point of what I'll say next is that not only you cannot cover the points with k lines, you cannot cover the points with k narrow cones. Okay. Yeah, let's take a break.
So we'll meet here, back here at like 11:45, 46, something like that. 5 minutes.
Okay. Right. So this argument proved that if you have a mapping that comes from k orthogonal vectors, then in this isotropic mapping, you have to have at least k distinct points. But in fact, it's also true that the points that you have cannot be covered by k lines. And the next observation is that those points cannot be covered by k narrow cones. So if you, I don't know, I can only visualize that in 2 dimensions. But this is saying that suppose you have a unit ball, a unit sphere. If you take a small region of the sphere and then look at the cone that intersects the sphere in that small region, and then you look at all the points in your map. So your mapping F is mapping the n vertices of the graph into n points in this k-dimensional space. And the norm square of those vectors add up to k. As we said, the norm square of the vectors along any line can sum up to at most 1, so that you need k lines to cover them. But also, if you look at a small cone, the norm square of the vectors in this cone, they will also have to add up to at most 1 plus epsilon, where roughly epsilon is the area, or so it's the
projections along that line have to add up to at most 1.
yeah.
So you're saying anything in the cone.
Yeah, so if the widest angle of elements in this cone is more than arc sine or arc cosine, whichever is right, of epsilon, if that's the narrowness of the cone, then each of those inner products will be at least 1 minus epsilon of the actual norm. And so if that adds up to 1, the actual norms, they add up to 1 over 1 minus epsilon squared. So it will be arbitrarily close to 1. Okay. So you need now, so if each of those cones can have, for a sufficiently small angle, if you look at an angle small enough that each cone can account for less than a 1 plus 1 over 2k fraction of the say 1 plus 1 over 2k L2 squared norm, and L2 squared norm has to add up to k, then k minus 1 cones will not be enough to cover all of it. So that will be the other thing, that you need at least a k plus 1 distinct cones to cover everything.
Or even all.
At least k. Huh?
We would say it's even true for a good fraction. If you want to cover almost everything rather than everything.
Yeah, where almost everything will have to be 1 minus 1 over 2k or something like that. Yeah. Okay. Yeah. So let me say just just one thing about how one proves the original Cheeger's inequality, because in our argument we want to combine these kind of ideas with that original proof. So in the original Cheeger's inequality, we have some eigenvector x2, and we have a small Rayleigh quotient. Let's say the Rayleigh quotient of x2 is smaller than epsilon. So x1 is the all 1 vectors, x2 is orthogonal to x1, and it has this small Rayleigh quotient. So the proof will show that there exists a threshold such that if we define the set S to be the number of actually no, let's do it a bit differently. So it can be shown that if you have two orthogonal vectors, each of which has Rayleigh quotient at most epsilon, also any combination of them will have a Rayleigh quotient at most epsilon. So this means that we can take our vector x2 that had this Rayleigh quotient smaller than epsilon, and we can shift it by, we can shift every coordinate by a fixed constant if we want. So we'll, I mean, again, this is kind of, there are some unnecessary complications, but it will make it easier to generalize. So we can get some modified vector that also has this small Rayleigh quotient, and such that the median of this vector is 0. Right? So such that it has at least actually, let's just say that the entries of this vector are already, that we have named the vertices of the graph so that the entries of this vector are sorted. And so we have that no, the entry n over 2 minus 1 is non-positive, and the entry n over 2 plus 1 is non-negative. And now let's modify it again by one of those two operations. We either take all the positive entries and make them to 0. Let's say either we take or we fix the first n over 2 entries to be 0. So in I claim that for one of those two modifications, the Rayleigh quotient, yeah.
Are they defined for the fixed one? For the you don't change half and you change half to 0?
Yes.
Okay.
Yeah, I'm just yes. I don't know why I wrote it this way. So I have this vector which is sorted. The median is 0, and now what I'm saying is just that I look at either taking the first n over 2 entries to be 0 without changing the other, or the last n over 2 to 0 without changing the other. Now, what happens to the Rayleigh quotient in those two cases? Well, the numerator can only get smaller because when you look at those differences, if you leave kind of the positive entries unchanged and the negative entries you move to 0, you're only reducing the difference. And you know, for entries that were both positive, they say both positive. Entries were both negative, they go to 0, and so they get reduced. And now, in terms of the numerator, in
The norm of x is just the norm of x prime is just the sum of the norms of x.
Of those two norms, yeah. So one of them must have at least half the norm that you had before. So So after all this, we can say that there is a vector, now let's just call it x, such that the Rayleigh quotient of x is at most 2 epsilon, and x has at most n over 2 strictly positive entries, non-zero entries. Yeah, actually, maybe we can switch signs. So let's say and then all entries. So if we pick the negative entries, we'll change signs. Okay. So now what we'll do is that we'll pick a threshold t. Yes.
Could you just quickly summarize what you did to get back to that x?
Yes. So first, I took possibly a linear combination of my second eigenvector with the all one eigenvector, and then I got a vector of small Rayleigh quotient that has 0 as a median. So in particular, it has fewer than n over 2 negative entries and fewer than or equal to n over 2 positive entries.
Add the median, the current median to all entries.
Subtract.
Sorry.
Yeah, subtract the current median to all the entries, so the new median will become 0. Then either set to 0 all the negative entries or set to 0 all the positive entries. One of those two things will will make the Rayleigh quotient go up by at most 2. So that will be, now change the sign if we got a vector with negative entries. So now we get a vector with greater than or equal to 0 entries everywhere. The Rayleigh quotient is at most twice the eigenvector that we started from. And the number of strictly positive entries is at most half of the total. Okay. So now we can show that there is a threshold t such that a positive threshold t such that if we define S to be the set of vertices in which the value of this vector for v is greater than t, then the expansion of so the number of the expansion is the number of edges with endpoints in different sides of the cut. So this is a 0-1 expression, so we could also square it if we want, divided by d times the size of the set. And again, we could square it if we want. So we can find a t such that this expression, which is like the Rayleigh quotient of the indicator function of the set, is at most square root of, I think in this case it's just the square root of the Rayleigh quotient of x. There may or may not be an extra factor of 2. And in fact, it's possible to show that if we pick t at random according to a certain distribution, the expectation of the numerator divided by the expectation of the denominator will be at most the square root of the Rayleigh quotient. And then an averaging argument shows that a threshold like this must exist. So this is showing that so if you have so if lambda 2 is at most epsilon, you can find a vector whose support, whose non-zero entries are less than n over 2 vertices and whose Rayleigh quotient is small. And then this fact says that if you have a vector of small Rayleigh quotient and small support, you can get a set whose expansion is at most the square root of that Rayleigh quotient, and whose size is such that the set itself is a subset of the support of that vector. So in this case, it will be less than n over 2. So now we want to use, and in this argument, so this argument works exactly as well if instead of having a vector, we have a higher dimensional mapping. So we could define a Rayleigh quotient of a higher dimensional mapping of vertices into, so a vector is a mapping of vertices into real numbers. We could think of, which is what we have in our setting, more generally a mapping of vertices into higher dimensional vectors. So then we could define the Rayleigh quotient of a mapping in this way. And then it is still true that for every such mapping, by picking a threshold and looking at the vertices whose norm is bigger than the threshold, after this mapping, we get this upper bound. I mean, this is true with exactly the same proof. And actually, it's not even necessary to go through the proof. From a function with this property, one can get a vector with this property. No, just by summing up the.
One of the coordinate vectors.
Yes, sorry. One of the coordinates of this f will have the property.
So do you want to, now it looks like you need to do some sampling, maybe? So you have this vector which has suffered around like 10 things, and let's say I do some random sampling to pick n over to n cases where the figure you might have a non-negative. Would that be enough?
The variance would be too large. And in fact, you can sort of see that this would correspond to trying to find a clustering of a graph by sampling vertices at random. That it doesn't take into account the structure of the graph enough. Right. So if we are just given the eigenvector of lambda 2 and we know the eigenvector of lambda 1, then what I described before gives a way of finding a one-dimensional mapping in which the vertices map to non-zero values are at most n over 2, and that will give us a set of size less than n over 2 with small expansion, and its complement will also have small expansion. Now I want to say that if you're given k eigenvectors, then we can find k different mappings which have disjoint support, and each of them a small Rayleigh quotient. Because then this will give us, then we can apply this theorem to each of those mappings, and we will get non-expanding sets which are subsets of the supports of each of those mappings. If those mappings have disjoint supports, we will get disjoint sets.
Yes, I have a question. I don't think that you can pick threshold sets such that the norm of the vector is
I
large.
think you want a coordinate to be large, right?
Because, for example, you can consider if you have let's say a disjoint graph with two components, and I give you just the vector all ones here and all minus ones here. Now there's no threshold cut where you say that the absolute value of the coordinate, if you pick it smaller than one, either you get everything or nothing. there should, I mean, yeah, so this has to be, the cut has to be somewhat more subtle when you're working with an embedding.
Oh,
Because this doesn't even work in one dimension, in a one-dimensional embedding.
So you have to do this trick of making everything non-zero. So you're gonna like say that f is always one octant of the, you know, the thing that f.
well, in the case that you're saying, you will never get a non-trivial set. So if your vertices are mapped to +1 or -1, then for various thresholds, you'll get either
Either everything or nothing.
yeah.
But that's incorrect, right? Because you should pick, you should separate all the ones and all the -1s.
That's right. So okay. So so let me put it this way: there is a subset of the support so we always start with functions that have a small support. And so like in the case, if your assumption is that the support is small, and then you pick a subset of that support by picking a threshold and then looking at vectors whose norm is bigger than a threshold, then I think it's true. No?
But I think what he was saying still would hold, right?
No, but okay, so
you're saying like before you needed to make everything non-negative. So where's the part where you're making everything non-negative?
it's not there. It's so here our expansion is the edges that go from S to S complement divided by D times S.
Right.
Right? So in his case, this conclusion would be, so in his case where the support is everything, because half the vertices are +1, half the vertices are -1. So then our subset of the support will be the entire set of vertices. And this expression will be 0. So then, because there is, if S is the whole set of vertices, there are if S is the whole set of vertices, then it is true that the number of edges from S to S complement is bounded. Because in particular it's 0. But so, but when you have a mapping in which the non-zero points are bounded, you can start getting some. Then here, since this set S will have to be a subset of yeah.
So you have not shown us how to modify, so how to get these k such functions.
No. I'm getting there. Yeah. Okay. Yeah. Okay. So. So what I have is a mapping in k-dimensional space in which the points cannot be covered by fewer than k Narow cones. Okay. So now my okay. So a first idea would be to try to find k regions, which could be actually each region could be a collection of cones. So this could be region 1, and then maybe another one would be some other pair of cones would be region 2, and so on. So I want to find k regions of Rk. As a first goal, let's say such that when I look at the mass of the points in each region, I would like this to be at least an absolute constant. That's because I know that in my Rayleigh quotient, the denominator is k. Now, suppose that I find k disjoint regions such that in each of them, this expression, which is like that denominator but restricted to the region, is at least an absolute constant. If I could also argue, okay, so then my first idea would be to say that my k mappings will be the original function multiplied by the indicator function of the region. So before, my regions were non-negative points and non-positive points. And I would set one of them to 0 and keep the remaining one. And then I would say at least one of them is at least half of the total in mass. So here I want to find k regions such that in each of them, if I do this operation, the denominator will decrease by at most a factor of k. So if I can also bound the numerator, the Rayleigh quotient will be bounded. So this part is easy because I can, let's say, just take every region to be a collection of lines. I know that in each line, the mass can be at most 1. So what I'll do is to kind of start collecting points along lines as long as it's kind of a first fit bin packing algorithm. I'll look at points and put them in a region as long as it doesn't add up to more than 1. When it adds up to more than 1, I'll put the next point in the next region and so on. So how many bins am I going to open to I mean, what's going to be the final outcome of this? It turns out that I need to have at least k bins that have to be at least half full.
You'll fill up before you go on to the next bin, you'll fill up every bin at least half full.
Yeah, let's say I do first fit decreasing. So then I open up a new bin only if the previous one was at least was almost half full. Well, I will need some property of those regions. But for now, just let's say that I want them disjoint. So if I get them disjoint, I can get each one to have mass at least a half. So it's the denominator of the Rayleigh quotient goes up by at most 2k. But I don't get any control of the numerator, unfortunately, because I could have two really close by regions. Or actually, I could have a region with one point that is really close by but outside, and another point that is really close by but inside. Now, in the numerator, this edge was giving a really small contribution. But when I say this region stays what it is, the rest of the mapping goes to 0, now this edge becomes really long. So the way we deal with this is to use some kind of smoothed indicator function to do this process. Yeah?
Can you choose the isotropy condition that no small region contains too many points?
No, that's fine, but it could still be that a region, in how I define it, can be a union. It doesn't need to be in any narrow. Right? Maybe this region contained these points, but this added up to a small fraction of mass. So I also picked some points here and some points here. And now there was a violating point here, a violating point here, and a violating point here. So what you would want to do is maybe to get the region a little bigger. But then it's easy to start losing a log n factor if you say, well, I'll make it a little bigger if it increases the mass by a constant factor. And then so instead what we do is to say, all right, so the points in the region will say what they are. Points far from the region will go to 0. And points in some kind of intermediate distance, we do something in between. So say if the distance is more than some threshold delta, the point goes to 0. If it's in the region, it stays where it is. If it has distance epsilon from the region, then it will be a linear combination of itself and 0 with coefficients that, it's just kind of a scaled.
That depends on the distance.
Yeah. So this will be basically 0 when the distance is more than delta, and 1 when the distance is 0, and the distance divided by delta in between, or 1 minus. Almost orthogonal?
They want it disjoint, it will be almost disjoint.
So what I want is that when I look at the distance between two regions, this should be at least some lower bound, so that when I look at the support of the support of those functions will be the original region plus this extra delta room in each direction that I need to smoothen the mapping. But how do we define this distance?
Will not be independent, not disjoint, the supports will not be disjoint.
No, they will. So we will pick the regions so that not only they are disjoint, but any 2 points in any 2 different regions have distance at least delta, or 2 delta. And then we will apply this delta smoothed indicator function so that if we construct this function with a certain region R, the support of this function will just be R and points a distance at most delta from R. Right, this smoothed indicator function, this is 1 if f of x is in R. It's 0 if the distance of f of x from R is bigger than delta, and it's what is it? The distance divided by delta in between. No, it's 1 minus the distance divided by delta. So the support of each fi is the region Ri plus all points at distance at most delta from it. So if we pick regions that are pairwise at least 2 delta away, will be okay.
But you might still have points in the support of one and in the support of the other that are very close.
No, so I mean that's true. We could have points in the support of one, point in the support of the other that are at distance 2 times delta. But then what will happen is that those points were at distance 2 times delta. Then after one of them goes to 0, they become a distance. Well, we'll define the distance so that the distance is always at most 1. Okay, so let me say how we define distance and how this affects the Rayleigh quotient.
So the regions will not cover all the points.
No, so no. In fact, it's important that they don't. So the region, they will have to have big gaps
But they
between
still
them.
have to cover a good
Yeah.
portion of the
Yeah.
constant fraction
Of the L2 square mass of the points, yes. Yeah. Okay. So the distance that we use, let's define it directly on Rk. So this will be the distance between the unit projection of Z and the unit projection of W. It's essentially the angle between them. Okay, and that's important because in terms of how this affects the Rayleigh quotient. So what's going to happen is that we have two. Right. So let's look at, say, for example, those 2 points. They have a certain distance whose square will contribute to the numerator of the Rayleigh quotient. Now, if this vector goes to 0, then the norm of this will contribute to the Rayleigh quotient. Okay. So this is bad whenever the distance between those 2 points is small compared to the norm of either point. And essentially this will and this will not happen if the angle between them is large. Because if the angle between them is large, then either they have comparable norm, and then their distance is comparable to either's norm, or they have different norms, but then in that case it's always true that their distance will be large compared to either norm. Okay. But but this is an important matter of scaling. So so those are 2 vectors that are very close to each other, but putting one to 0 is okay. And those are vectors that are farther from each other, but putting one to 0 has a bigger effect. So the advantage of using this kind of distance is that it measures how bad it is to put one vector to 0 in terms of the numerator of the Rayleigh quotient in a scale-free way. Okay. And the other advantage is that since it talks about the angles, it's also true that in our isotropic mapping, you cannot have too much mass of points concentrated within points that have small distance from each other, because that would mean that you have all those points that are in a narrow cone, and we did a calculation before that this cannot happen. Okay, so there is a calculation that shows that if that sort of for every delta, if f has a small Rayleigh quotient, this function will have a small Rayleigh quotient, provided that we'll have a small. If the function has a small numerator, this function will have a small numerator. So we are left to figuring out what's happening to the denominators. So to find regions of space that are disjoint and well separated according to this distance, and that account for most of the points. So that's okay. So a simple way of doing that is to so let's say that we take the unit sphere in Rk, and then we do okay, so in 2 dimensions it doesn't give the right impression. But so we'll divide the sphere into, we'll partition the sphere into small regions. So one way to do it in general is to go by kind of latitude and longitude, or by taking a tessellation of the space into small cubes, and then the intersection of the sphere with those cubes. So we just need those regions to be small. Then we'll scale down each region by a 1 minus epsilon factor. Okay. So we'll look at the same thing, but maybe with slightly smaller cubes. Okay. So that will leave gaps in between. But if this epsilon is something like 1 over k, where k is the dimension, those gaps will account for only a constant fraction of the surface of the sphere. Okay. Now, okay, so now that's what we start from. We have this small region of the sphere that have gaps between them, but the gaps add up to, say, less than half of the total surface of the sphere. Now apply a random rotation, and now let's look at what points fall in the gaps and what points don't. Well, the fraction of points that fall into the gaps, on average, will be proportional to the area of the gaps. So a few points will fall in the gaps. So let's look at now those cones, which are the cones that intersect the sphere at those regions. So all those cones will have this nice separation in our definition of distance, because for every point in two different cones, their unit projection will belong to a different region of the sphere, and the regions of the sphere were chosen to have a little bit of distance between them. Now, those cones are small, so each of them can contain at most a 1 plus epsilon total of L2 square mass. So we said a line can only contain at most 1 in L2 square mass, but a little cone can contain at most 1 plus epsilon. So then we can do again the beam packing argument, and what we get is that we can find k collection of cones such that each of them adds up to at least now maybe it's 1/3 of L2 square mass, so that we lose only k in the numerator. Okay, so then it's k squared there because we lose k in the denominator, but then we also lose a 1 over delta, and this delta has to be chosen to be 1 over k for the regions, for the gaps, not to count for too much of the surface of the sphere.
You have to pick cones that are next to each other?
Not in the analysis. I mean, intuitively, you would expect that those final non-expanding sets will correspond to connected regions of space, so that the points that you will pick will be close to each other. But in our analysis, that's not necessarily. I mean, we expect this is what happens, but it's not forced into the analysis. Potentially, you could pick far apart cones.
Maybe you could gain in the k squared exponent.
Yeah. Presumably, this would have to be done in order to not to lose this factor of k.
What is the lower bound of the? What is the best possible thing about?
You could hope to get log k instead of k as a loss.
You try and analyze taking log k random hyperplane. Maybe that's what gets
Yeah,
you
but this is not scale free. Somehow you could imagine that your correct regions, like one of them is very narrow and one of them is kind of fatter, and when you randomly partition the space, somehow it's hard to imagine that there is a way of finding the k regions that doesn't look at the mapping, because there could be some something that you would easily miss unless you actually look at the points and see that a lot of points are concentrated in one place.
Two clusters that are close together.
You wouldn't separate them, yeah.
So is there any connection to rounding algorithms for given kn, where you also lose, you have this loop log k factor, for example. In some sense, it's, I mean, when you round these vectors that you get from the SVD group, it's some sort of partitioning of space in some way. So is there any parallel, or is there a deeper connection between these?
This is a rounding technique. I mean, you're somehow using your f's to do. You're trying to round them off into that.
That's true. I mean, the difference in the unique games, you
You have an ensemble of three vectors.
right. So you're still rounding to Boolean values, because then those the rounding on those vectors will tell you which of the k values you want to assign to a variable. But there is still a rounding to a 0, 1 kind of solution, which is not so. Yeah, maybe it's also.
Saying like you're mapping the space to one of k values, rounding off. So it seems like it's very related.
So maybe let's think where the log k is coming from in the two cases. So here, our log k comes from doing a dimension reduction from k dimensions to log k dimensions, because our main loss is coming from the number of dimensions. Well, there is also a loss here. There is a number of sets in the denominator, but there is a whole different rounding algorithm doesn't suffer from that. But we also lose a k from the dimension, which is that we need to pick this delta to be 1 over k, because if you're trying to sort of cover a k-dimensional space with small gaps, those gaps have to be small as in 1 over k. So if we map f to be a mapping into log k dimensions, we improve that dependency. So what we want is a mapping into log k dimensions, which is kind of isotropic, so such that it's still true that any narrow cone contains only a small fraction of the points. So we do that just by a kind of Johnson-Lindenstrauss dimension reduction. But so there are n points, so there are n squared distances, but we still want to use only log k dimensions. So the point is that if there is a cone that violates this condition, this can happen in various ways. It could be that there is some huge vector that belongs to this cone, and then this will have, and that vector by itself is skewing up the mass of the cone. But then, so this seems already that it's asking you to use log n dimensions, because even one vector having big violation of distances can cause a cone to have excessive weight. But then if one vector has excessive violation, those violations are really big, so then we can use large deviation bounds in a distance that you get by dimension reduction and say this is happening with really low probability. Or maybe you can have two vectors, each of them contributing too much. That also, for each of those two vectors, that's very unlikely, although you have to double up because of the union bound. Okay. So in fact, in the end, it's enough to have a mapping into a constant number of dimensions to have a constant violation in what's inside each cone. But we want to get close by some kind of 1 plus delta, and to do that you need log 1 over delta dimensions. That delta has to be 1 over k, so that's where the log k. Okay. So this is in this seems to be a different log k than what's coming up in the rounding of unit games.
So let's have further questions over lunch.
Okay.